tonight on confirmation and conditionalization.
Thanks, Angela. Thanks everyone for coming. I want to talk, well, my goal is to convince you of something which I hope you find surprising, namely that a certain principle is false that is, to my knowledge, universally accepted in philosophy, almost universally accepted. And it's this principle that's with which the handout here begins, which I call evidentialism. It's the view that one should believe things to the extent that they're supported by one's present evidence. Sounds harmless, so my goal is to convince you that this is false by a very old-fashioned method, by giving a counterexample. But that will take some setup. So the counterexample will sort of be in section 7. Until then, we need quite a bit of setup. So I'll begin by, well, let's begin by clarifying what the principle actually says. Maybe there's a reading on which it's true, but I mean something quite specific by this evidentialist principle, and I put it here on the handout in terms of these sort of pedantic, this equation. So if you look at it on the left-hand side, it says, maybe I write it so that people on TV can also see what's going on. So what it says on the handout is cur AT of H. What is that? This is the degree of belief. So the evidentialism is the view about linking degree of belief with support by the evidence, right? We should believe things to the extent that they're supported by the evidence. So one part of this is the idea that you have degrees of belief. You believe some things more strongly than others. And this is the degree of belief curve for credence of some agent A at some time t. Degrees of belief vary from agent to agent, from time to time, so hence these sub and superscripts. Can mostly ignore them, but, well, the t will become relevant, the A will know. But just to remind us that this is some person's degree of belief, not something free-floating. So, degree of belief of agent at time in some hypothesis, that's what this says, equals conf H given E A T. So what does this mean? This is supposed to mean the degree to which the evidence, which the agent has at time t, confirms the hypothesis or supports the hypothesis. So far this is not something very specific. I haven't defined what one of that's supposed to be, but so this is just meant to capture what the slogan, you should believe things to the extent that they're supported by your evidence, surely also assumes that there is such a thing as the extent to which evidence supports some hypothesis. So this is just a way of writing this in the pretentious, sort of formal way. So this is the shape of our target, and I'll argue that this is false. That, well, just to give it away, it's not sort of universally false. It's almost always true, but there are some sort of edge cases where it's false. Okay, so now let's talk a bit more about the left hand and the right hand side. So on the handout, we're already in section 2. Oh yeah, so a little side note. All these things to clarify. So first, evidentialism is a normative claim. So it doesn't state this as a descriptive hypothesis, but it states this as a prescription. Right? So the claim is your degrees of belief, you, the agent A at time t, should equal so that's the hypothesis. We're looking at this normative claim, not this descriptive claim. All right, clarify that now. If you're familiar with sort of orthodox subjective Bayesian confirmation theory, you may notice that in Bayesian confirmation theory, confirmation is usually explained in terms of somebody's degrees of belief, which suggests that this equation is actually trivial, because we cash out what it means for a hypothesis to be supported by evidence by looking at some particular agent at some particular time and see to what extent the agent's degrees of belief sort of make the hypothesis probable given the evidence. And this suggests, as the evidence is known at that time, that the two are then equal. This suggests that this whole thing is trivially true, is empty, wherefore the prescription that it should be true is an empty prescription. Prescribes something that's true by definition, which would make evidentialism an empty claim that I certainly wouldn't have any counterexamples against. So in a sense, by offering a counterexample to this claim, I also offer a counterexample to this version of Bayesian confirmation theory, which would not allow for any counterexamples because that would be true by definition. But that also means that I need sort of to have a starting point where we don't already assume that confirmation just is sort of degree of belief. Otherwise, I couldn't possibly give you sort of a counterexample. If you always substitute confirmation by the agent's degree of belief, and well, you'll never be able to see a counterexample. But fortunately, I think we are able to sort of imagine cases in which intuitively, at least, somebody violates the principle of evidentialism. So intuitively it can easily happen that somebody believes something to an extent to which it is not supported by their evidence. So we do have an independent grip on the left hand and on the right hand side. So imagine a case where you're in a jury, somebody's in a jury for some sort of murder case, and the only evidence is there's an eyewitness and they saw some tall person emerging from the scene of the crime. Not even clear whether that tall person committed the murder, they didn't see anything else, and that's the only evidence there is. And there's this accused person who is tall. And so there's one jury member who is, in light of this evidence, absolutely convinced they're guilty. We would think, well, no, that's irrational. If this person is not adequately responding to the evidence, the degree of belief is high that this is the guilty person, but intuitively that is not adequately supported by the evidence. So we have a sense that the degree of support that the guilty verdict gets from the evidence is low, although the degree of belief is high. So I think we have an intuitive grip on confirmation which isn't immediately tied to whatever agent we're talking about and their degree of belief. Or think of climate skeptics who are sort of aware of the evidence and nevertheless are pretty sure there is no climate change happening. That seems irrational because all the evidence points towards that it's happening. So we have a grip on what is supported by the evidence, which seems at least at first glance independent of what somebody believes. So I start with this, for now, sort of intuitive idea that we can estimate roughly to what extent a hypothesis is confirmed by the evidence. I will assume, however, to make this sort of a candidate for being true, that this confirmation measure is a conditional probability measure. It's a very weak sense in the sense that if you conditionalize it on any evidence for which it's defined, you get back a probability measure, because I do assume that rational degrees of belief satisfy the probability axioms. So this would be immediately out if this confirmation measure, conditional on some evidence, wouldn't satisfy the probability axioms. So I assume this is not terribly important for my talk, but I assume that we can cash out confirmation, which is sort of this half theoretical thing we have sort of some independent grip on, but it's not quite clear what it even is supposed to track. And I assume that this can be cashed out in some probabilistic terms. I think there are good reasons to do this, which have to do with the success of probabilistic approaches in confirmation theory. I won't go into this here, but so that's the background here. Why I think this part of the principle is okay, that this has to be the right form to stand on the right-hand side of the equation. Oh yeah, I should maybe also mention here, I assume for simplicity that this is a determinate, unique probability measure. That actually strikes me as quite unrealistic, but it's something that just won't matter for my topic today. So what that means is that a probability measure assigns some precise number to any inputs for which it's defined. So we could plug in here the evidence we have for climate change and the hypothesis that climate change is happening, or that if we do nothing, the Earth will warm to such and such an extent, some precise hypothesis, and our evidence. And then if this is a probability measure, it has to output one precise number, right? 0.79532217, and so on, up to absolutely precise. And that seems a bit odd, that confirmation is so stringent that sort of it's absolutely precise for any input for which it's defined. I'll assume it for simplicity. So nothing would change if we say more realistically that this is sort of an interval measured function that sort of said, well, the evidence supports this hypothesis to sort of between 0.5 and 0.8. That seems more realistic, more adequate to handle real life cases. Won't matter to my argument, so let's just pretend that it's absolutely precise. All right. Oh yeah, by the way, one might wonder what evidentialism says if this is not absolutely precise. Presumably what it says is that the degree of belief should fall within that range. That would be sort of the way to adjust it. And that, if you adjust it that way, we can sort of run the arguments that I'm going to make. One can also say that this is not absolutely precise. And then it gets even more complicated. Good reasons to think that this is also not precise, because degrees of belief also aren't defined to any decimal place. And then everything gets a bit more complicated still. So that's not just assuming we don't have these complications, because they'll just make everything a bit harder to see, but the arguments really rely on. Okay, so much for the right-hand side. Let's talk about the left-hand side. We're in section 3 in the handout. So I assume I already mentioned that degrees of belief satisfy the probability axioms. So this is a version of Bayesianism in sort of the minimal sense, in which Bayesianism says that rational degrees of belief should obey the axioms of the probability calculus, which is, yeah, one could talk about it, but I'll just assume it for now that that is correct. There is a second aspect of Bayesianism, though, which will be important, which is the idea how degrees of belief change when new evidence comes in. And so the orthodox Bayesian answer is that they change by the rule of conditionalization. So the background assumption here is that information comes in by way of sort of, there's something externally happening that's not something that's modeled in the framework, but somehow new information comes in, and in the simplest case, which we're looking at here, the information is not doubted. So the agent just accepts that that's true, and the question is, how do we adjust the rest of the degrees of belief? There are things to say about when the evidence is not taken as certain, but again, for simplicity, we don't consider that case here. So some evidence comes in at some time. And now what are the new degrees of belief? Somehow they should adjust. And there's this very abstract formal rule for how that goes, which is the conditionalization rule. And what it says is, we write exactly the same way here. Credence T A in H should equal credence A T in H given E. Oh, T minus 1, I guess. Yeah. So it says, so we sort of, for the purpose of this, we assume that there's the time t minus 1 before this evidence came in, and there's the time t when the evidence came in. So it's sort of a discrete step. One could make this continuous, but it wouldn't really do sort of any purpose here. So there's this time with which the evidence arrives. This is the evidence the agent has at time t. We didn't have it before. And now the new credence, the new degree of belief in H is the old degree of belief in H conditional. So that's the old degree of belief in H on the supposition that E is true, which is conveniently defined by the ratio formula if that's defined H and E A T divided by E. If these are defined, then that equals the ratio. In any case, there are these conditional beliefs, and the new degree of belief is just the old one conditional on the new evidence. There are arguments for why this is the right way to it's a very abstract, as I said, a very sort of, it doesn't really say anything in particular. So here I am, I have those degrees of belief. How should I respond to this evidence? Well, here's sort of the very abstract level response. There are reasons to believe, good reasons, I think, to believe that this is the right way to respond to evidence. There are arguments, kind of related actually to the arguments for why one should have degrees of belief that satisfy the probability axioms. There are sort of Dutch book arguments that you could be money pumped if you didn't update in that way. There are arguments from the principle of reflection. There are arguments from minimal revision, which I find the most convincing. I'll set them aside here, so just there's a literature on this, and some of you may be familiar with it, that this is the right way to update beliefs. It also won't really be terribly important that you have a clear sense of what this even does. We'll see where it measures in a bit. Okay, one thing that's also on the handout is that something follows from this immediately if beliefs change in that way. So again, this is a prescription, right? So this is how beliefs should change. It's not some sort of prediction about how they do change. It's a prescription. I think all equations that we have are prescriptions. Anyway, so this is conditionalization. And let me erase this because it looks too complicated. Quite simple. Okay, so one consequence of conditionalization and the probability axioms is that, what I wrote on the handout as well, is that this equals credence 0A in H given E1 and Okay, so what is 0? 0 is not the Big Bang, but sort of some time before the agent has started collecting the evidence. And so if you look at their history, so hypothetically, we have an ideal agent who always updates by conditionalization. And in this case, it's true that their degree of belief at time t, in some hypothesis, equals their degree of belief at the starting point, before they had any evidence in the hypothesis, conditional on, and here's all the evidence they received. Evidence at time 1, time 2, time 3, time 4, time 5. Conjoin them all up to time t. and this is sort of their degree of belief. Sort of makes intuitive sense that the latest degree of belief is sort of the starting point, updated on the conjunction of everything that ever comes in. It follows from this and the probability axioms. So, but it's worth keeping that in mind for reasons I'll get to soon. So I put it sort of in words on the handout. An agent's belief at any time, if they're ideally rational, then their degree of belief at time t can be sort of factored into these two components. There's the absolutely prior beliefs, their priors, which they started, and the total evidence they receive at all times. So that's sort of the way we can factor how the final beliefs are determined. Okay, still in the setup. Now consider this alternative to evidentialism, which is in section 4, and I should write it as well. So there's an alternative way of cashing out the idea that degree of confirmation is linked to degree of belief, and it's this E prime thing, which says that the agent's prior beliefs in any hypothesis that was made conditional on any evidence should equal conf of H given E. So if you think about it, this is actually kind of plausible. This means that sort of an agent who doesn't have, imaginary agent who doesn't have any evidence yet, their degree of belief in some hypothesis on the supposition that the evidence is true should equal the extent to which the evidence actually supports that hypothesis. That sounds plausible. In fact, that's true, I think. So I think this principle is true. So E prime, I think it's true, but E is false. So these are subtly different. And I think this is the right way to think about confirmation. This is incidentally how Carnap defines confirmation in his later work on inductive logic. So he says, let's sort of imagine an ideal agent updating by conditionalization, wheel back all their update, sort of undo everything they've learned. You arrive at sort of a prior belief function that doesn't really already know anything about the world, and the confirmation function is their degree of belief function. And he assumed that it's unique, but he already noticed it doesn't necessarily have to be. But so this is a nice approach sort of to understand what confirmation is, which doesn't mean it's sort of an entirely free-floating thing. It has nothing to do with degree of belief. We can link them in this way. Maybe it's a definition of this. You could also say this is a definition of that, right? So I'm thinking of it more like sort of this is a way of getting a firmer grip on something we have sort of a vague pre-theoretic understanding that this equation holds. All right. So now I can already give some hand-wavy arguments against E, against the evidentialist doctrine. Here's one. Notice that, so on the handout I've labeled these things, let me also label them. So this is E, evidentialism. This is conditionalization. This is E prime, sort of a variant of evidentialism. So one thing you can notice is that evidentialism and conditionalization have the same thing on the left-hand side, but rather different things on the right-hand side. And this is a way for the two to come apart, right? So you can easily see how they can come apart. For example, change the agent's previous beliefs at time t-1 without changing what is supported by evidence, right? So just change what the agent believed in the past, hold fixed what's supported by evidence, why would that be affected by changes to past beliefs? And then these two give different verdicts. Right? So then they can't both be correct, because if the agent previously, before you make the change, satisfied both of them, then afterwards they no longer, because this makes the new beliefs depend on the previous beliefs which you've now changed. So that will be different, whereas this will still be the same. So this is a way for the two to come apart abstractly. It's not, I haven't given you a case to think about what to do in this situation. And there's a bit of literature on what one should do in this case, but the verdicts are unclear, so I can't give you sort of a, I mean, do you then give up C or do you then give up E? It's not really clear what you should do. They're kind of weird cases. So this is a case to look at if you want to check it be true, because you see that it can play with conditionalization. And as I mentioned, there are very good reasons for conditionalization. So to the extent that these reasons also apply under variations of the prior beliefs, this means these are reasons against evidentialism. But as I said, it seems to me they're not very conclusive, because if you look at the cases, I've at least never come up with a really good case that convinced anybody. So this is not a case.
Sorry, can I ask a question?
Yeah.
Because if you like, maybe you'd like me to ask a question when you finish.
Yeah, when we do them.
Okay.
Mind, sorry.
No.
Yeah, I mean, we can say absolutely clarificatory question.
Yeah,
Totally.
I still don't understand what the first
Yeah.
expression on the right is. What do you mean by confirmation? Confirmation
Yeah. Okay.
I can think of incremental or absolute.
No, I mean neither of this.
Yeah,
what I mean
I understand that.
This is a number that measures the extent to which this evidence confirms this hypothesis.
Yeah, but when you say confirm, you mean in terms of rational credence?
No. I mean, so I think we have to postpone it to the end because that's not. Okay. So as I said, I assume we have some pre-theoretic sense of that this evidence supports this hypothesis to some degree. And as I said, I'll assume this is a probabilistic function that sort of puts further constraints on what we mean. So maximum support is 1. Maximum sort of
But is that objective?
We have some grip of this, I've assumed. I have not assumed anything else yet. And in fact, sort of, I'm inclined to follow Carnap, as I said, and say, well, this is a good link. So to the extent that I think there are objective constraints on what one should believe without any evidence, these are also objective constraints on conf. If there are precise constraints and they fix every question that is answered by conf, then conf is objective by this link. I don't really need much of this, but so this is how I think of it. Yeah. What was I going to say? Another case in which one might think evidentialism, this E hypothesis, can be false. What I wrote on the handout here is these three together imply that evidence is cumulative in the sense that later evidence always implies all the earlier evidence. Let me try to show why this is so. So this is another principles are blue. Let's see. So we have. How do I do that? We start with your. Does it write properly? So credence 0 in a hypothesis given. Let's take the agent's evidence at time t. This is a non-rigid designator, so a bit careful. So this is just whatever the evidence is at time t. By this principle, this is conf h given e a t. This, by evidentialism, is the agent's degree of belief function. At t in a, they're an ideal agent, they're updated by conditionalization and arrive and satisfy this, so that should be their degree of belief function. But we know from this fact here that if they're conditionalizing, then this is their prior degree of belief in H given the conjunction of all evidence they ever received. 1 and T. So C H is, that's just this thing, I copied it down here. So what we get, sorry in the way, what we get in any case from these three principles is that the prior credence of the agent in H given the evidence at T equals the prior credence of the agent in H given the whole of their evidence they ever received. How could that be true? I mean, it could be true by coincidence, but how could it be systematically true as would be required if these principles are systematically general rules? Well, only if these two propositions are in fact equivalent. And that would mean that ET is sort of enough to reconstruct the whole history of evidence. Which is a bit curious. I mean, one might think that evidence can be lost. One might think that an agent's later evidence can be more sparse than something they learned along the way. Maybe forgetting is one obvious way how an agent's later evidence. It's a bit hard to think about these things because what exactly is evidence? So that would be a big other topic which I'm kind of ignoring. But intuitively one might think that evidence is not always cumulative in that sense, that the later evidence is sufficient to sort of reconstruct the whole history of evidence. And if it isn't, then one of these three must be false. And now which one? We can choose. Conditionalization is false, this prior sort of form of evidentialism is false, or evidentialism is false. This is the main reason why Tim Williamson thinks conditionalization is false. I think he made the wrong choice. Evidentialism is false, and conditionalization is true. But you see that there's a tension already here. So since evidence is not cumulative, and as I said, it's sort of in this basic picture, the evidence is not something that's entirely under your control. That's something you have or don't have, and if you're unlucky and it's not cumulative, what should we give up? You have to give up something. And I think the right thing to do is to drop evidentialism. Other people think the right thing to do is drop conditionalization. But there are good reasons for conditionalization, and I think in these cases there are reasons to drop evidentialism. Again, not obvious. I went now through some examples. From my experience, people don't have very clear intuitions. You sort of see something must go, but you're not sure what must go. But I just want to sort of soften your maybe sort of attitude towards evidentialism, that this should be an obvious truth by noticing, well, look, if evidence isn't cumulative, then something must go that also seems very plausible. And here is how this arises. Now, let me work towards the argument that is my main argument. So, first, a bit more setup. There's some kind of cases for which it's widely agreed that conditionalization doesn't quite work, and they have to do with so-called self-locating knowledge and self-locating evidence. So this is evidence not about what the world is like, but about where you are in the world, or what time it is, or who you are in the world. This arises, for example, in cosmology, if you think about sort of multiverse hypotheses, according to which reality divides into these large pockets or bubbles of sort of self-contained little universes, and it can easily happen that in these models that two universes agree to a large extent up to a certain point, let's say. And so there's this other universe somewhere out in reality, and there's somebody else giving a talk there, just like I, uttering the same sounds. And the whole history in that that universe up to now is the same, but they might diverge later. Suppose that happens now. Assuming that I believe the universe is like this, the question arises, who am I? Am I the guy in that first universe or the guy in that other universe? They're both sort of within the same reality. And if they differ in the future, that makes a big difference, right? Suppose I know the universe contains these two indistinguishable up to now locations where I might be, and one will be hit by a meteorite tomorrow and the other not. Now, what's my degree of belief that I'll be hit by a meteorite? It's uncertainty, but it's not uncertainty about the world. I know what the world is like. It's uncertainty about where I am in the world. And to handle these kinds of cases, it turns out, for reasons I won't be able to explain, that we have to somehow tweak conditionalization. It doesn't quite work for these kinds of cases. Here's the tweak. Very simple. We add a plus sign after the A. It's very simple. So this is not a further index, but rather an operation on the credence function, which sort of transforms it so that what it does is it moves the center of every centered possible world wanting to the future. It's not important what it does, actually. I just tell you that this is a way to adjust it. What we'll need is an instance of the rule, and there is pretty much no disagreement on the instance. That's why I'm not explaining the rule to you. So I'm just telling you that there's a way to adjust it. It is, I have to say, not universally accepted. It is, in fact, only accepted by Chris Leacham and myself. But it's the correct rule anyway. Okay, now I can come to the... Right, so the point of this adjustment is that once we do this, then these three can come apart even if evidence is cumulative. So I'll have an example which doesn't rely on any kind of forgetting or anything like this, where the three can come apart and where I think evidentialism is the one that has to be given up. Right, you will become quite impatient by now. When is the counterexample coming? It's still not coming, but we're in section 6. We're almost at the counterexample. Now I'll go on a tangent and talk about quantum physics. So many of you will know that quantum physics is weird. It's very successful, but it's also weird. And what's weird about it is that it says that physical systems can be in superposition states. I'll get back to my topic, just bear with me. So just a bit about quantum physics. So quantum physics says that physical systems are sometimes in superposition states where it looks like two contradictory states of affairs are simultaneously true. So suppose you shoot a photon at a half-circled mirror, so there's a mirror that's kind of half transparent. And what happens, quantum physics says, is that the photon gets reflected with a certain amplitude, and it goes through the mirror with a certain amplitude. So it is both here and there. It's here with amplitude square root of minus a half, and it's there with amplitude square root of a half. So amplitudes are numbers, they're complex numbers. They have a size and a direction. And nobody really knows what that's supposed to mean. The photon is there with a number, and it's over there with a number. In the old days, people thought, well, it's either here or there, and we just don't know where it is, so the numbers are somehow probabilities, and one of them is true and the other false. And it turned out that's very hard to make sense of that. It can be basically empirically refuted. So somehow in reality, the photon is there with a number and here with a number, and that's peculiar because one doesn't really understand what that means. And now, quantum mechanics if you don't tweak it, also suggests that when now somebody goes and measures the position of the photon, then the measuring instrument and the person looking at it also enter into superposition state. So they will measure the photon being there with a certain amplitude, a certain number, and they'll measure the photon being over here with a certain number. And then people thought that's odd because that's not what we experience. We don't seem to measure photons at two places with different numbers. One doesn't even know what that would be like. But people thought that's not what things are like, so people started crippling quantum mechanics and said, there must be something else we're missing. There must be sort of an entire other layer of reality, which is what Bohmian mechanics says, or there must be something, we must somehow add a new law to the Schrödinger equation, which says that these whole branches of superpositions collapse, which is what collapse interpretations do. It occurred to Everett, and actually before him, to Erwin Schrödinger, that actually just normal quantum physics without sort of any additions or modifications does make sense of our experience. Because if you think of what happens at the two branches of the superposition, so here you measure the photon to be over there, you can sort of see what happens to the measuring instrument, what happens to the person. They're just a physical system. We're just physical systems. We're in there. You can see that this physical system, which is us looking at the measuring instrument, will have absolutely no interaction with the other branch. That is something that's predicted by standard quantum mechanics. So if this is just how reality really is like, you wouldn't expect there to be anywhere in reality somebody who has bizarre experiences of things sort of being in two places at once. Rather, you'd have these two observers, both somehow us, weirdly, that observe something, and it seems to be just in one place. And here it seems to be at the other place. And why does that contradict our experience? So that's why Everett and Schrödinger suggested, no, let's leave quantum mechanics as it is, and take it seriously, not just in some instrumentalist sense, accept it as delivering the right measurement outcomes, but that's what reality is like, which is certainly counterintuitive, is this idea that reality constantly branches in a certain sense. So before we shoot the photon, there's just us, let's say, and this one photon, and as soon as it hits the Hasselblad mirror, or maybe as soon as we measure, there's a bit of disagreement how to spell that out, we, at least the photon earlier, but we certainly have sort of branched into two people, one measuring there, getting these different outcomes, and never interacting with one another. So that's the Everett interpretation. Now let's get back to our topic. Consider a case where you're not sure the Everett interpretation is true, you're not sure it's false either. So for simplicity, your degrees of belief are split, what did I say? If you assign the degree of belief 1/3 to the Everett interpretation, and 2/3 to some collapse theory, to some alternative to Everett. And you also, I see, well, something with spin. In any case, so I should have done the photon. So you do some experiment, some quantum mechanical experiment, which has two possible outcomes, up and down. Doesn't really matter what it is. So two outcomes, up and down. And on the collapse hypothesis, there are two ways the world could be. On the collapse hypothesis, there's one thing that will definitely happen. There's no branching going on. So one possibility, which sort of I drew in this diagram, is that you'll get an up measurement. You're now here before the measurement. Another possibility, which I draw like this, is that you'll get a down measurement. So what this is supposed to symbolize is you're here in the world, and as time passes, in the unique future of this point, there's an up measurement. So this is a possible scenario. You're here, self-location, and if you're here, then there'll definitely be up. If you're here, there'll definitely be a down measurement in the future. And if some collapse version of quantum physics is true, then one of these is real. So, but you don't know which. So let's say you give credence a third to this possibility, like to being here, and a third to being there, because you haven't looked at the measurement outcome yet. And this is our collapse hypothesis. Let's say GRW, so the leading collapse hypothesis. Right? It's clear what I'm drawing here. So these are two places where you could be, and in their future, there's either an up or a down measurement, and your credence is divided between those two. Together it's 2/3 because you're only 2/3 certain that your W is true. There's a third left. The third that's left goes to Everett in quantum mechanics. If that's true, then you're here, but there'll be both measurements in the future. There's this branching weirdness going on, and Everett. So this also has a third. Well, why a third? Just so, whatever. We could take any other numbers. That's just to make the case simpler. So we assume your print is divided in that way. You're 2/3 certain in GRW, 1/3 in Everett. And now what should happen if you observe, measurement is done, you observe spin up. You observe this up result. So we're either here or here now. Clear we're not there. Clear we're not there. Where should the probabilities go? There's only one sensible answer for where they can go. The answer is that this must now have probability 2/3, and this must now have probability 1/3. Takes a bit of thinking through why exactly that's the only right answer. And this is the only use, well, almost the only use I need of my great revision of conditionalization. It actually gives you those results. But while this is controversial, this result is not. I've never met anyone who doubts that this is the right update. And this is discussed quite a bit. It matters for average and quantum physics that people change their beliefs in this way rather than any other. And you can see immediately why. Because notice that, I mean, the one obvious alternative that comes to mind is that you could say this is a half and this is a half. That's something one could say instead. Why? Maybe because, well, there are two possibilities. If they're equal. I mean, so I'm not clear why that would be right too, but that's sort of one main alternative. If that's, however, how you change your mind, then notice that you become more confident in the Everett hypothesis through this measurement. It goes from 1/3 to 1/2. Whereas your confidence in GRW goes from 2/3 to 1/2, so it goes down. So if it went that way, that would mean that by making measurements, you would become more confident in the Everett hypothesis. And it would go on. And in fact, if you think about it, these branching events don't just happen in measurements, they happen all the time. They're constantly happening as I speak, according to quantum physics. So just by looking at you, I should become increasingly confident in the Everett hypothesis, no matter where I started from, which is patently absurd, right? So surely, one needs a way to update one's beliefs. This is why pretty much everyone agrees with this way of updating, where this kind of scenario doesn't help to distinguish between Everett and GRW, and the only way to not do that is to have a third here, 2/3 there. And this way, this leaves intact that before this measurement, I was 1/3 certain in each UM and 2/3 in GRW, and it's still the same afterwards. There are more systematic reasons for why this is the right update, having to do with why this is the right rule. But for now, let's just accept it. As I said, I've never met anyone, and this occurs in print quite often, and everyone agrees that's how it should go. Finally, here's the counterexample. All right, pretty much the same, except that simplifying a bit, getting rid of the quantum mechanical complications, and moving all these possibilities into the same world. So, scenario, there are 3 duplicate solar systems in the universe, a kind of multiverse type scenario. So, the universe is very big, and it has 3 pockets where we might be at the moment. Here they are all. So this is all in one universe. 3 places where we might be, 3 galaxies, solar systems that have up to now been duplicates of one another, and we don't know where we are. So let's say, in this case, quite reasonable, 1/3 equal. No further evidence. We know that the universe is like this, but we just don't know where we are. The future of these solar systems is, however, quite different. What happens tonight is that one of them will enter the up nebula, which is purple. So if you're here and you look up the night sky, into the night sky, tonight you'll see purple. This one enters the down nebula, which looks green, let's say. So you'll be able to distinguish them tonight. You just don't know yet. This one will fission. This one will weirdly, by any means you can imagine yourself, something like perfect style personal fission or whatever, teleportation, quantum physical way. This, in any way you like, will fission into two future solar systems, and one goes in the up nebula and one in the down nebula. So if you're here and you look in the purple sky, in the sky you see purple and you see green. You see, structurally this is just like the Everett case, and so the belief update should also be the same. So if you previously were 1/3 certain that you're in this fissioning region of the universe, it should not go up by the same kind of reasoning as before. So we know this is how the probabilities should go. And now, this is of course no longer GW and EGM, they're just different hypotheses about in which sort of sub-region of the universe you are. Okay, and now, so you knew that we have believed in this hypothesis, H is 1/3, but I claim the degree of belief to which, the degree to which this hypothesis is confirmed by your evidence is 1/2. Why is that so? Well, look what your evidence is. Now you later evidence, you're now somewhere here. So, well, in fact, you're either here or here, right? You can't be there because you see the purple sky. What is your evidence? Your evidence is the purple sky. Your evidence is all your memories. You never forgot anything. So imagine somebody else is now born in that galaxy, and you tell them all you know. Before you start telling them, they're undecided where they might be. Here or here, give half-half each, seems the rational thing to do. No particular evidence yet, half-half. Is there anything you can tell the person that would sway their indifference, that would convince them, oh yeah, we're more likely to be here? No. The only relevant difference is that this possibility has this branching history. Why does that make it less likely? Why is that evidence that suggests, yeah, then we're not here, because in the past that thing branched? Why is that irrelevant? That seems completely irrelevant to where we are. So I think the degree to which that hypothesis is supported by the evidence at that time is a half, not a third. If you disagree, tell me what the evidence is that really supports this more strongly than that. I just can't for the life of my sort of see. And notice that half and a third, a third of, or 2/3 are sort of closer to each other. But we can have more branching and drive these closer to 1 and to 0. So you would need a lot of evidence when you think that these are rational beliefs. But what would the evidence be that makes it rational to give this 0.99 and this 0.01? I just don't see any sort of evidential difference. So that's the counterexample to this claim, because the extent to which you should believe H is a third, is it? Yes, a third, but confirmation with confirmation here is half. All right. To wrap up, well, okay, so E is false because I constructed a bizarre counterexample. Why should you bother? I mean, obviously, this is not something that happens all the time. This has very little relevance to criticizing people for not accepting climate change, or sort of coming to rash conclusions in juries. I grant all that. This has pretty much no practical relevance, but it's theoretically interesting. It's theoretically important in philosophy. For example, as I mentioned, because it seems to be a counterexample to the most straightforward and the most popular version of Bayesian confirmation theory. This is the dominant approach in confirmation theory, which assumes, maybe even trivially, that these are identical. But they're not. So we have to sort of be more clear about how we cash out sort of confirmation. This sort of partly goes back to the question sort of what is this? Well, it's not just degree of belief, because the two can come apart. Otherwise, so we have to be careful. They're linked. I think they're linked, for example, in that way. So it's not two entirely different things. But we have to be careful, because any counterexample is enough to show that they can't be true by definition, right? So we must sort of take these to be things of which it's at least an open question whether they agree or not in a particular case. It also matters, for example, when people like Jim Williamson or Isaac Levi want to replace conditionalization with this evidentialist equation. If that equation is not generally true, that's a bad idea to say this should be our new rule and we give up this because of evidence can be lost. It's not a good idea if this principle is not always true. And even if it's just true under some weird circumstances, that's enough, I think, to show that that's not a good move. Also, I think once we see that the principle is false, we might reconsider sort of the strength of it when we consider sort of cases where evidence is lost. So maybe once we've already allowed exceptions, maybe these are exceptions. That's my attitude, that we just allow further exceptions. One other reason why one should bother with this bizarre counterexample is that it's not actually quite that bizarre if we take seriously Everettian quantum physics. Because something like this, I just told you, happens all the time. If we take Everettian quantum physics, not if we believe it doesn't really matter that somebody fully accepts it, but as soon as we sort of assign some positive credence to Everettian quantum physics, which seems to me to be sort of a rational attitude, then this sort of scenario happens all the time. There's sort of a fission possibility, Everett, there's an non-fission possibility, collapse, boom, whatever. And then we have to be very careful not to assume without argument or just assume that this evidentialist principle holds. And there is actually, so there's a large literature on one particular problem in the Everett interpretation concerning with the justification of the Born rule. And in that whole literature, it is always assumed that this principle is true. But that's exactly the kind of case where I think we have to be very careful not to assume that the principle is true. And I think it's worth going through that literature and seeing exactly where it relies on these sort of diachronic considerations, that how beliefs should change over time, and what is supported by the evidence at later times. And it's always assumed that will give the same verdict. If you start with reasonable prior beliefs, update, you get to some beliefs, and these beliefs coincide with what's supported by the evidence. But these are exactly the kinds of cases when sort of a fissioning scenario is involved. This we talk about Everett, where I'm not saying the principle is always false, but these are cases where the principle can easily become false, so we have to be careful if you're interested in that kind of thing, not to just assume that always holds. That's it. Thank you very much.